Good morning, everyone. Welcome back. So I was asked to do a series on combinatorics with a focus on the sort of combinatorics sort of tricks that might help you in interview, or just the combinatorics stuff that would be useful to know for interview math. So like when you're being interviewed, obviously interviews are coming up now for university admissions and things. So I thought I'd go through probably in like a 5-part series, but then I'll probably do more parts where I actually go through specific problems. So like in the first 5 parts, I'll just talk about like the different principles that exist and that are useful to know. And then after that, I'll probably look at some questions specifically. There are some interesting questions from places like Crux, AOPS, things like that. If you're not sure about Crux is Crux Mathematicorum. I'd definitely check it out. Very nice article. The first section, Mathematic, has some nice combinatorics questions. And there's a couple that I remember doing that I think would be nice to look through, because some of them involve things like recurrence relations and things like that. So it's sort of like not just basic counting cues that we'll look at today, but more sort of mixture of things, which I think would be nice to look at. And we'll also look at some other hard combinatorics problems then. But for the first video today, I want to just talk about counting cues. Obviously, combinatorics is all about counting. Okay, it's effectively, in some senses, it's how do we efficiently count things. Like how many ways are there to do something, and there's probably going to be a very, very large number of ways. So you can't just list that thing out you can't list every single possibility out. You have to have an efficient way of counting, or an efficient formula that's going to just generate that number for you, as long as you sort of do the calculation. And so there are sort of 4 types of question, as we'll see, where there is just a formula that you can effectively memorize. And it's very unlikely, I will say, that you'll get these types of questions that I'll talk about today in an actual interview, because they're just a little bit too simple. But still, knowing this is very useful, because typically these things do come up as maybe steps in an interview question, or maybe they're sort of they're in disguise a little bit. So you have to do some logic first, and then arrive at sort of a point where you can calculate how many combinations there are, using some sort of choose, or using some sort of multi-set argument. I mean, I don't know, but definitely knowing this is the core of combinatorics I want to talk about today. So I think it's a good place to start. Okay, so the first question that I want to ask, and do pause the video when I ask these sorts of questions, do pause the video and see if you can do them. The first question I want to ask is, how many 3-character passwords are possible? So how many 3-character passwords are possible if each of the first 2 characters is one of the 3 letters, so capital A, capital B, or lowercase g. Okay, and the last character is one of 5 or 6. So it's just a number, 5 or 6. Okay, so this is the first type of question which you sort of need to be able to do. You need to be confident with in combinatorics. And once you sort of learn the sort of formula to sort of do these types of questions, it becomes fairly routine. And like I said, you're unlikely to get a question as simple as this in an interview, but it's a good place to start. Okay, so how would we answer this? Or what is the way to sort of reason through this? Some of you might know the formula, but I guess we need to talk about how do we reason through it if I didn't know the formula, and if I had never done this type of question before. Well, the first thing that I would know for sure is that the first character has the 3 options, right? So the first character is either obviously capital A, capital B, or lowercase g. Okay, so any password is going to begin with one of those 3, because I've specified that each of the first 2 characters is one of those 3 things. Okay, so specifically the first character, that's what we want to focus on, is one of those 3 things as well. So any password must begin in one of 3 ways. So any password begins in one of 3 ways. Okay, so obviously in the first of which is just starts with the letter capital A, and then there are 2 more characters, or it could start with the letter capital B, then there are 2 more characters, or it could start with the letter lowercase g, and then there are 2 more characters. Okay, so at this point we have sort of 3 options. Okay, and each of these corresponds to a different password, right? Because the first character is different. Now the next character we know is also going to be one of capital A, capital B, or lowercase g. So the next character, right, is also capital A, capital B, or lowercase g. And so knowing this will increase the number of possibilities by a factor of 3, and I'll illustrate why, because it is important to also know necessarily intuitively why that happens. So this fact increases I'll just do an arrow like this. That means increases the number of possibilities by a factor of 3. By a factor of 3. Okay, and the reason for this is because, well, just starting with the letter capital A, right? There are 3 scenarios for the second character, right? Just ignoring the third character yet, we haven't looked at that. But just for passwords where the first 2 characters are either A, capital B, or G. If we were to say the first character is capital A, then we'll have 3 different passwords, right? One where the second character is also capital A, another one where the second character is a capital B, and one where the second character is a G. So that's why it's increasing by 3, because this is true for all of them, right? Because we're allowing repetition, okay, of characters, so we could have capital A and then capital A again, right? And so similarly for capital B, you would imagine that there's going to be capital B, then capital A, capital B, then capital B, or capital B, then lowercase g, right? These all correspond to different passwords. So that's why there's a factor of 3, okay? Because effectively there are 3 options for the second character, okay? And so for each choice that I've made for the first character, that's fixed, okay? It can be whatever it wants. But once I've made that choice, definitely making the next choice, there'll be 3 options for each choice of my first character, right? And there are 3 choices for my first character. So obviously you'd see that there's going to be 3 times 3 choices, so 9 choices for passwords where the first 2 characters are going to be either capital A, capital B, or lowercase g. Okay, and then obviously if I finish this, we can have this, we can have this, or we can have this, okay? And so it should be fairly, obviously the last character has to be a 5 or a 6, okay? But, you know, it should be fairly obvious then that that's going to increase the number of possibilities by 2, because for each of these possibilities, okay, there will be 2 corresponding possibilities, one where the third is a 5, and one where the third is a 6, and those are 2 different possibilities. So from each of these, I can generate 2 extra, so I'm just doing this times 2, 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 and I'm adding them all together, right? Which is why, basically, what I'm going to be doing when I'm choosing my final digit is I'm going to be multiplying all of these possibilities by 2. Okay? So the last character, move to the right. I never get it right in terms of how much space I need to just, so we're going to have to just create boxes as we go, but the last character must be a 5 or 6, okay? And so this fact increases, so this increases, that up arrow there, which means increases number of possibilities by a factor of 2. And hopefully you can see what those sort of different possibilities will be, given that we have these 9 possibilities over here by a factor of 2. Okay? And so, you know, if we have 3 possibilities for the starting, the next choice will increase that by a factor of 3, and then the final choice increases that by a factor of 2. Then what I effectively have is 3 possibilities to start off with. I multiply that by 3, right, to get the number of possibilities where I have just the first and second character chosen, and then multiply that by 2 to get the number of total possibilities, right, because then I've also chosen my third character, right, because each of these 9 possibilities here, will correspond to 2 possibilities, one of which the third character is 5, the other of which the third character is a 6. So I'm going to be effectively multiplying this number here, 9, by 2, to get the total number of correct passwords that I'm looking for, which is 18, right? And so, and we can obviously also write 18 as 3 times 3 times 2, okay? So that's kind of the important thing here. So thus, there are, you know, 3 times 3 times 2 is equal to 18 possible passwords. Okay, not that many, but yeah, you know, we obviously don't have much choice for the characters, so that's why there's not that many. But you know, you could easily generalize this question, right? And say, oh yeah, instead of just having capital A, capital B, or lowercase g as the first 2 characters, I could have any of the entire alphabet. Let's just suppose it's in uppercase. Then I have 26 options, right? So then what it becomes is effectively I have 26 starting options. Then for each of those 26 starting options, that will branch into another 26. We'll have 26 times 26 to represent sort of the number of possibilities where the number of passwords of the first 2 characters are just uppercase letters of the alphabet, right? So that's 26 squared. And then if I just keep the 5 or 6 the same, then I will increase it by a factor of 2 for the same reason that we increased it by a factor of 2 here. So that gives us 26 squared times 2, which is 1,352 possible passwords, okay? And obviously, the more choice you have, the more number of passwords you're going to be able to generate, right? Makes sense. Obviously, on an actual keyboard, like on a computer, you have like numbers, letters. I mean, yeah, it's there's going to be sort of millions, billions, probably way more than that, to be honest with you. Otherwise, that would be quite easy to search, maybe. But there'll be like a very large number of possible passwords you can make. There's also special characters. You can use lowercase, uppercase. Yeah, there's a lot that you can do with passwords. So yeah, that's and the reason why there's so many passwords on a computer is because there's just more options, right? So anyway, okay. So now we need to be a bit specific and try and generalize these sorts of things. Okay, so we'll look at objects called lists. So counting lists. Okay, so in combinatorics. A list is effectively an ordered sequence. So a list is an ordered sequence, effectively. An ordered sequence of objects. Okay? So that's just how we define a list. And I'll go through some examples in a bit, but effectively it's just some sequence of objects, right? And the order of those objects matters. Okay. Yeah, I mean, for example, like the password that we just looked at, right? So the order of sort of the letters, the order that they appear matters, right? Because a password that starts with capital A and then has a capital B is completely different to a password that starts with capital B and then has a capital A. Okay, so even though they've utilized the same letters, for example, these two passwords are different because of the fact that the order is changed. Okay, so this would be you could represent passwords as lists effectively. Okay, so just boiling things down, right? Because in combinatorics sometimes you get questions where they invoke some sort of context, but you can sometimes boil things down to just lists. Okay, which is the most fundamental sort of objects in terms of whenever order matters, like in these scenarios, yeah, so whenever order matters, you can pretty much most of the time. Well, I don't know about most of the time, but you can sometimes condense problems into just condense sort of objects into just being lists, and then deal with the related problem to do with lists that you've probably learnt. If you've done combinatorics, as I'll talk about today, I'll talk about those things. So a list is an ordered sequence of objects. Okay, fine, and we define and we define a k list to be a list of length k. Okay, a k list to be a list of length k. Okay, so yeah, as I've already spoken about, in a list, the order of which the order in which objects appear does matter. So in a list, the order in which objects appear does matter, but it does very much matter. Okay, so you're going to get two different passwords from two different orders effectively. So a password is just like a list. And the other important thing that we care about is repetition. A list doesn't necessarily, I mean, you can choose whether or not you want your list to care about repetition. Okay, so you can say an object can appear more than once in a list, can appear more than once in a list. Okay, unless forbidden by the constraints of the problem. Unless forbidden by the constraints of the problem. Okay, awesome. Some people may also call lists words, but that's not really important. Just sort of whatever you want to call it, you can call it. I'll probably stick with the list, but if you want to call lists words, you can as well. And maybe you'll see that being used in other sort of combinatoric scenarios. That a list, effectively an ordered sequence of objects, is just called a word by someone, and that's fine. Obviously, going through just a couple examples here, right? Not the most important thing, but still, these are quite fundamental objects, so it's good to be exposed to them. Obviously, this would be an example of a list. So basically, like a sort of like a finite sequence, effectively, right? So we have -2, 3, and obviously the order within a finite sequence does matter, right? So effectively, if I swap -2 and 3 here, that's going to give me a different sequence. So this is like a 2 list. We say this is a 2 list because it's a list of length 2. And a valid 3 list would be something like this. So it doesn't actually have to be obviously numbers inside the list, just anything you want. And in this case, we have x, y, and z. And if I were to swap y and x, I'd get a different list. Okay, so this is a 3 list. And I may be allowed to, if the question allows it, or if the question permits it, which it did in this case. It did permit repetition, so we're allowed to repeat sort of the letter capital A twice, or the letter capital B twice, or the letter lowercase g twice. So lists may allow repetition. So I may be able to do like x, y, y, z. And then that will become a 4 list. Okay, so it will change the length of it, but it may allow repetition, or it may not allow. The question may not allow repetition of elements within a list. So maybe x, y, y, z, the list containing those 4 elements, the same as this list here, x, y, z, the list containing the elements x, y, z. So yeah, just stuff that you need to sort of determine from the question whether repetition is allowed or not, and whether order matters or not. We'll go into cases where it doesn't. So far, you've only looked at cases where order does matter. But if you're in a case where order does matter, then you may be able to basically distill any context and just talk about lists. So most combinatorics sort of counting problems where order does matter can just be like broken down into problems about lists, as we'll see as well in the video. Okay, so the other important, well, I guess another thing that's worth mentioning, not necessarily too important, but still worth mentioning, is that you might hear the term n-set being used, and all that means in terms of today's video and in general combinatorics, if you see this, effectively we define an n-set to be a set, right, of size n. Okay, a set, if you don't know, a set is just a collection of objects. So typically use these sorts of curly braces and then just put a bunch of objects inside, I guess. Slightly abnormal, but that should be fine. You don't need to be too rigorous about sets, obviously, for things like interviews. Just know what a set is. And effectively, yeah, a set is just a collection of objects. So this would be an example of a set. but sets don't allow for the repetition of certain characters. So if I were to repeat 5 like this, then that set would be the same as the set containing the elements 4, 3, and 5. So those two sets are the same because repetition isn't really allowed. Like, you can do it, but it's not going to change anything. So it won't make a difference, effectively. And the order as well of terms in a set does not matter. So you can swap 3 and 4, so you get 3, 4, and 5 like this. That's the same set as 4, 3, 5. Okay, so those are just the two key facts that you need to know about set. But we'll cover that as well a bit later in the video. But that's just a little intro for people who aren't familiar with sets. So an n set is just a set of size n. Okay, by size n we just mean it has n objects inside it, effectively. Okay, right. Okay, so in general we have so this is the first sort of formula that I want to cover, the first sort of important formula that I want to cover. Okay, so suppose that I want to find the number of effectively k lists taken from an n set. Okay, so for example, an 8 list, so an 8 character password is just an 8 list. It's just a list of length 8, okay, because the order of terms matters, as we've already seen. And we're also allowed to repeat elements, at least for this problem. Okay, let's just imagine a problem where you are allowed to repeat elements for the sake of the argument that I'm just going to make. So passwords, 8 character passwords are just 8 lists, okay? And let's suppose that each character has to be an uppercase letter from A to Z, okay? So then there are going to be, effectively, you're taking each character, you're making a choice, you're picking an element from the set of size 26. So from a 26 set, effectively, of just uppercase letters. So, yeah, so those are the types of scenarios that we can easily generalize, that are about to easily generalize. So the number of k element lists taken from an n element set. Okay, so effectively we have a list of length k where each element in that list is taken from some set of size n. Okay, so if this is the case, then the number of possible lists that we can make, okay, is always n to the power of k. Okay, it's always n to the power of k. And remember that order matters, okay, for lists, because we're dealing with lists here, so the order matters. And in this specific formula, or I guess trick, I'm assuming that repeated elements are allowed. Okay, so if we have lists where the order, obviously the order will always matter with the list, but where repeated elements are allowed, okay, and we're choosing each character of the list from a set of size n, okay, then the number of possible lists we can make is n to the power of k, okay? So for an example, right, the number of 8 character passwords, this is what I was talking about, the number of 8 character passwords, remember each password is just an 8 list, each 8 character password is just an 8 list, a list of length 8 effectively, right, because the order matters. So the number of 8 character passwords, for which each character must be an uppercase letter, for which each character must be an uppercase letter, is by the formula, right, is going to be 26 to the power of 8, right? Because effectively we have an 8 list, right, that we're trying to construct. We're trying to find how many possible passwords exist. So basically how many 8 lists are there, right? And each element is some element in the set of uppercase letters, effectively, right, of which is size 26. So we're trying to find the number of 8 element lists from a 26 element set, okay? And so using our formula, that's just going to be 26 to the power of 8, okay? And this should also, intuitively, hopefully, you should also understand why this is. Because if we go back to our example, imagine that, in fact, we had, let's just say, a 3-character password, so a 3 list, right? And we only allowed uppercase letters, okay? Then our formula says that there'll be 26 to the 3 possible passwords, which makes sense, right? Of course, there'll be around 26. Of course, there'll be exactly 26 to the power of 3, because for my first character, I'll have 26 options, right? It could be any of the uppercase letters from A to Z, so A, capital B, capital C. So I'm going to have 26 possible passwords just from the first character, right? And then for each of those passwords, I'll have another 26, right? So just started with capital A, I'll have another 26 more. So I'll have capital A, capital A, capital A, capital B, capital A, capital C, so on and so forth, right? And then the same for capital B, the same for capital C. So for each of those 26 starting cases, I'll have another 26 that I'm forming. So actually I'm doing effectively 26 times 26, right? I'm increasing the possibilities by a factor of 26. And then again, for each of those new 26 squared passwords, I'm going to have another 26 cases. So I'm going to get 26 times 26 times 26, which is just 26 cubed, which actually evaluates to around 17,000 possible passwords just from 3 letters, which could be any uppercase letters that you want, okay? So yeah, already getting quite large there. Well, it's not very large, but definitely not large enough, but still larger than the type of number of passwords we had before. Okay, so hopefully you can see what this is saying intuitively. Okay, right, so now we need to introduce something called the product principle. You probably heard this before in maybe GCSE further math, if you learned the product rule for counting. It's going to be a little bit more rigorous, a little bit more of a rigorous treatment of the product rule for counting, but it's saying the same thing. So it's not the most important, but it's still a principle that is, well, it is very important to combinatorics, but in terms of memorizing the details and the rigor here, it's not the most important thing for you. Maybe later on when you're at university, that will be more important. Okay, so the product principle. I mean, it's fairly sort of intuitive, this principle, I would say. You maybe didn't even think of it as a principle too much, but it is. Effectively, what it says is, if I'm trying to count, so in counting the number of possible lists of length k, right? So k lists of the form, effectively, L1, L2, all the way up to LK. So just lists of length k with some like k different characters in them, effectively. So just, yeah, lists of length k. If I'm trying to count how many possible lists of length k exist, remember for lists, order matters. And we don't necessarily care for this principle whether or not repetition and so on and so forth. But if I'm trying to count the number of possible k lists of the form L1 all the way through to LK, right? If, firstly, if there are C1 ways to specify the first element of the list. So, for example, I might have 26 possibilities to choose my first character for my password, right? So in that case, C1 would be 26. Because if there are C1 ways to specify element L1 of my list, right? So again, I'm going to need to make a box here to specify element L1. Okay, got this. Specify element L1 of my list. Okay, L1 of the list. So if there are C1 ways to specify element L1 of the list, right? So that's just the number of choices you have for the first element in your list, right? And each different option that you choose leads to a different list. Okay. Which it will for the case of a password, right? Each different starting letter corresponds to a different password, okay? The only scenario where it wouldn't might be, I mean, this doesn't really matter that much, but the only scenario where it wouldn't be something maybe like in graph theory, where you have points in space and you have edges connecting those points, right? So the edge connecting this point to this point is the same as the edge. So if I have 2 points in space and I have a line connecting them, right? The edge connecting the first point to the second point is the same as the edge connecting the second point to the first point. So we typically describe edges using ordered pairs and things. So if I were to have a list of just possible edges, effectively, and then I had 2 different ordered pairs that mean the same thing. Okay, so they would technically look different in terms of the list that I'm creating, but they're telling you the same thing. So like if I were to define the ordered pair 1, 2 to mean this is the edge between the first and second point, that is effectively telling me the same thing as obviously the edge between the second point and the first point. So if I started my list with this, right, it'd give me the same effectively thing as if I started my list with this, even though they look different because they mean the same thing. So unless you have a scenario like that, then pretty much always each different option for your first element will lead to a different list, effectively. So if there are C1 ways to specify element L1 of the list, okay, and each such specification leads to a different k list. Specification leads to a different k list. Okay, so if that's the case, and this other thing is the case, so for every other list element L subscript I, so for every other sort of character in your list, there are, if it's also true that for every other character there are, some number of ways, we'll call it C subscript I, it doesn't need to be the same as C1, right? Like for example, in our password from before, obviously there were 3 ways to choose the first character, but effectively only 2 possibilities, like 2 choices for the third character, right? Because we can only choose the numbers 5 or 6. So in certain scenarios, in that case, C3 was 2 because you could either choose for the third character 5 or 6, but C1 was 3. So C1 doesn't need to be equal to Ci in general for all I, right? For any I, it doesn't need to be equal. So for every other element in your list, we'll say that there are Ci ways to specify that element. So effectively, there are that number of choices for whatever that element is going to be in your list, right? No matter of the specification of the previous elements. So what that means is that regardless of what happens in my first and second character here for my password, that there will always be 2 possibilities for the third character, 5 or 6, right? It's not going to be the case that in some cases there's only 2 possibilities for the last character, and other there's 1 or something, right? In some combinatoric problems that might happen. Those are more advanced combinatoric problems. But for the basic product principle, we assume that isn't the case, so that there'll be the same number of choices as there is in this case with the password for the third character or for any character, regardless of the characters before it. So okay, so no matter the specification. Sorry, what I should say. No matter the specification of the previous elements. Specification of the previous element. Of the previous elements. Since we're dealing with element Li, the previous elements are L1, L2, all the way up to L subscript I minus 1. Okay, so no matter how many sort of options there were for those, right, whichever sort of specific list we choose, there's still going to be the same number of ways to choose the ith one, the ith element. Okay, and so we also assume that each specification of Li will lead to a different k list. Okay, and each specification So the same thing as we're talking about for the first case, right? So except in this case, a scenario where that might not necessarily be true is, let's say that is something like when I'm trying to choose, say, a subset of effectively size k, say. So effectively, if I have subsets of a set and I'm trying to determine how many subsets of a set of size n, right, of an n set, how many subsets of an n set are there with only two elements, for example? Well, there would be n choices for the first one, right, for the first element in my subset, right, because it's an n set, right? By the way, for anyone who's not sure, a subset is effectively defined such that each a set is a subset of another set. Every element in that set is also in the other set. So, for example, if you have a set A like this, 1, 2, 3, 4, and I have a set B like this, 1, 2. B is a subset of A because every element in B is also in A, right? That's how we define subset. So you can determine whether a set is a subset of some other set by determining whether each element in that set is also in the other set. So that's the notion of subsets, okay? And so if I were to have a set with n things inside it, I would have n options for the first choice of element in my subset. Because remember that in sets, there's no repetition of elements, right? And so what that means is that the second element, I'll have n minus 1 choices, okay? And what this product principle is going to say is that, oh yeah, we should be able to just multiply these to find the number of possible subsets, effectively, of size 2 from an n set, assuming that, so first of all, the first thing that we assumed was that there are C1 ways, in this case C1 is equal to n, there are n ways to choose the first element of our subset, which is true because there are n things in the set as a whole. So the number of subsets of that specific set that we're considering, of length n, the first element that we choose is going to be n choices, right? And then at that point, so we've chosen one element and we can't repeat elements, we have n minus 1 choices remaining, right? And so the second part here that we're just writing here is saying that, for each other element Li, there are Ci ways to specify that element. I should have said Ci ways. So for each other element Li, there are Ci ways to specify that element. No matter, effectively, what happened before. So no matter, which element I chose first, there'll always be n minus 1 elements to choose second. That is true. But the next part that didn't, which I haven't finished yet, is saying that each such specification leads to a different k-list. That isn't true in this case, okay? Also because, really, subsets, you can't really treat them as k-lists. In fact, they're subsets, right? And so effectively what that means is order doesn't matter there. And so you can't really say that each choice of second element leads to a different k-list, or because first of all, subsets aren't k-lists, and second of all, if we did somehow try and make a subset a k-list, we'd run into a problem because a subset, for example, containing the element 1, 2, is exactly the same as a subset containing the element 2, 1. So even though the specification of my first choice, there was n choices, and each of those will correspond to a different subset, each of these choices, each of these n minus 1 choices does not. Okay, because if I chose 1 first and then 2, that's the same as if I choose 2 first and 1. Okay, so n times n minus 1 will not give me the number of possible subsets of size 2 from a set of size n. We'll talk about this problem in more detail later in the video, but just for now, you can see that that's a scenario in which, for example, even though there are, say, this case C2 might be n minus 1, so there are n minus 1 options for the second element in my subset, right? Each specification of that doesn't lead to a different subset, right? Because I could have a 2, then a 1, or a 1, then a 2, right? And those are the same subset. Okay, so I can't just do n times n minus 1 to give me the number of subsets effectively. So yeah, that's why it's also important that So for each other list element Li, there are Ci ways to specify that element, no matter the specification of the previous elements, and that each such specification. Why is my spelling so bad? I hope I haven't been doing that the whole video. And each such specification of Li leads to a different k-list. Okay, then what the entire point of the product principle is that it says if all of that stuff is satisfied, then the number of possible k-lists that we have are exactly C1 times C2 times all the way up to CK, right? Then there are CK such lists, or C1 times C2 all the way up to CK. And so this is sort of the idea, right? Especially with the password as well. The password cases, we use exactly this sort of principle, right? Because we had C1 choices for the first character, and then the second character increased the number of possible k-lists by a factor of C2, which was also 3 in our case. So we did 3 times 3, or C1 times C2, and then we had C3, so k was equal to 3 in our case, because we were looking at a 3 list, so a password of 3 characters is just a 3 list. Okay, so we had C1 times C2 times C3, and in our case C3 was just 2, because we had 5 or 6 as the last character. Okay, so we use the product principle implicitly, in our previous problem, and it's usable quite a lot, but you do need to have lists, first of all. So we're counting k-lists, okay, so sets are different objects to lists, so be aware of that. So if you're dealing with sets, then order doesn't matter, okay, so you can get some overlap, as I showed you with the subsets, okay, And just make sure that all of this stuff is true. Okay, so for example, that there aren't two ways of specifying the same element. So for example, the edge from 1 to 2 being the edge from 2 to 1. And that effectively there's not some cases where there's two options for the third character and some cases where there's one, then you can't use the product principle. Yeah, also make sure that each specification, each different option of some character will give you a different k-list. So yeah, just make sure that all of those things are true. And if all of those things are true, then you can use the product principle. But in practice, you're not going to do that, right? You're not going to just go through each point bit by bit. Effectively, you need to be able to sort of just know this in essence. I mean, when I've used the product principle before, I've never done this, and most of the time I've applied it correctly. That you can sort of tell intuitively whether you're not applying it correctly, because I mean, you don't even necessarily need to know. Oh yeah, I have to apply it only for lists. Say that you tried to apply it for a subset, okay? Then you should think to yourself, wait, am I overcounting? And the answer would be yes, because you can have two subsets which are the same with elements reversed. Okay, so you need to think about that yourself. But if you know this principle, then it kind of tells you in a sense. You don't need to. You can avoid thinking about it directly. But in those problems that I've done, I've always sort of thought, oh, right, I'm overcounting by applying the product principle here because I'm dealing with sets, or because there's some special cases that I haven't considered, so that doesn't quite work in the way that I thought it does, or there's two different ways of specifying the same element, or, yeah, effectively, two different choices lead to the same k-list, right, for some li, okay? And those are really the cases which will basically cause this to crumble, but if all of these things are true, then the number of possible k-lists will just be c1 times c2 all the way up to times ck, okay? Hopefully that makes sense. Okay, so then talking about subsets, actually, the next sort of thing that I wanted to look at was a method of counting subsets, okay? So let's introduce a question here. So question, right? How many subsets of an n set are there? So I've already introduced what a subset is, but a subset is, so a set A is a subset of some other set B, if and only if each element in A is an element in B, okay? So that's effectively how we define subsets. So we have a set A and a set B, has some elements inside it, whatever, okay? But A is a subset of B if for each of these elements, it's also in A, it's also in B, effectively, okay? So that's just what a subset is. I mean, we've already seen an example of that in the video. So the question then is, how many subsets of an n set are there? And some of you may know the answer. It's quite a popular problem, okay? And it comes up as well, I'm sure, when you'll start university maths, and the first thing they'll talk to you about is things called power sets, which are basically just sets of all subsets, effectively, of a set. So I give you a set, there's a certain number of subsets you can create from that set, then you can store all those possible subsets in a larger set, and we call that the power set. But that's kind of not important in this, okay? But it's effectively related. So how many subsets of an n set are there? Now this is quite a famous problem in combinatorics, okay? And there's a really, really nice, I think the way that, I've seen it being solved that I'm going to talk about here is quite interesting because of the method, not necessarily the result. So, for example, if we take n equal to 3, right, let's just deal with a specific case first. And we also take a specific 3 set, okay, so the actual elements in the set don't matter, it's just the number of subsets, right? So if we take a specific 3 set, let's say the set containing the first 3 natural numbers, so 1, 2, and 3, right? Then what we can actually do is we can encode each subset of this set as a binary number, okay? So, so what we say is that we can associate effectively each subset with a 3-digit binary number. So if you don't know about binary numbers, effectively they're just numbers in what we say base 2. So decimal, or the numbers that you're used to, are in base 10. So for example, the number 121 is 1 times 10 squared, add 2 times 10 plus 1. Okay. But in base 2, we only have 2 digits, 1 and 0. Okay. And effectively, we can create numbers sort of similarly to this, except instead of the 10s here, you replace those with 2. So effectively, in base 2, you might see a number like this, okay? And this reads as 1 times 2 cubed, add 1 times 2 squared, add 0 times 2 to the 1, okay? Add 1 times 2 to the 0, which is just 1, okay? So that's base 2 or binary, okay? And you only use 1s and 0s in binary, okay? And then you can display any number that you want basically, yeah, in binary. So this formula here, 1 times 2 to the 3, add 1 times 2 squared, and so on. That's how you would basically, this is the number in base 10, right? Once you compute that, that'll give you the number in base 10. But effectively, that's what you're doing in base 2, right? You're assigning effectively this sort of value to each place, right? So this on the far right, this is 2 to the 0, this is 2 to the 1, and you just keep increasing the exponent by 1. Okay, 2 squared, 2 cubed, 2 to the 4, 2 to the 5, and then you place a 1 or a 0 there, depending on whether you want that in your sum, okay? So if I have 1, 1, 1, 1, that's 2 to the 3 plus 2 to the 2 plus 2 to the 1 plus 2 to the 0, okay? Right. There's definitely more to be explored. Binary is very fundamental, right? Especially in things like computers and computer science. But in terms of just the fundamentals, that's what it is. That's how it works, okay? That's all you really need to know for this. So what we can do is we can associate each subset, right, with a 3-digit binary number, a 3-digit binary number. And I'll denote that binary number as sort of a string here. So just D1, D2, D3, okay? Where specifically, I'm going to have to introduce another box here because I don't really want to run over too much. So yeah, we can introduce each subset as a 3-digit binary number, specifically where di is equal to 1, okay? Because remember, in binary, you either have the digit being 1 or 0. So it's equal to 1, effectively, if I is in the subset, okay? If I is in the subset, and di equals 0 if I is not in the subset. Why is this bugging out? If I is not in the subset. Okay, and so via this reasoning, therefore, just as an example, by the way, if I have a set of size 3, this is my set, containing the elements 1, 2, and 3, one possible subset I could have is this, right, containing the elements 1 and 2, and that will be represented by the binary number 1, 1, 0, okay? In this case, D1 is equal to 1 because 1 is in our subset, okay? D2 is equal to 1 because 2 is in our subset. D3 is equal to 0 because 3 is not in our subset, okay? So we've managed to represent this subset with a binary number, and you can do this with all of the subsets in your set, okay, including the empty set, right? The empty set is actually a set with nothing inside it, and that will be represented by the element 0, 0, 0, okay? And that is considered to be a subset of every set, okay? Because technically everything within that set is also in the larger set because there's nothing in there. So it's a bit of a degenerate case, but we do consider it in maths, and that represents the binary. And it makes sense here why we consider it, because think about it, like this represents a unique binary number 0, 0, 0. That is still a binary number. 0 is still a binary number, so we still count it. And then obviously 1, 1, 1 is the case where you have just the set itself, and that is also a subset of itself. So you will have unique binary numbers for each of the possibilities. Okay, and so the question then boils down to how many 3-digit binary numbers are there? Okay, because clearly there are as many subsets of size 3 as there are 3-digit binary numbers. And in general, if we were to extend this, and instead of a set of size 3, I chose a set of size n, then there would be as many subsets of size n as there are actually n-digit binary numbers. And so, by the way, binary is actually quite useful during combinatorics. Maybe we'll see it come up a little bit more, but being able to use binary and just sort of simple ones and zeros to represent more complicated problems is actually a skill that can help you. In this scenario, obviously, you already knew how to do this, so you probably already knew the answer to this, you already know the answer to this problem, but nonetheless, you can see how useful in this scenario binary is. But it might not seem very useful to you, because all we've determined so far is that for a set of size, for a subset of size n, effectively, from an n set, right? So if you want to find the number of subsets of an n set, then there will be as many subsets, effectively, of size n as there are n-digit binary numbers, okay? And when I say of size n, all I'm talking about is specifically the set that we started with. So there are as many subsets of a 3 set as there are 3-digit binary numbers. Similarly, there are as many subsets of an n set as there are n-digit binary numbers, okay? And you might think, okay, fine, but this is just sort of like telling us not necessarily anything if we don't know how many n-digit binary numbers there are. But what we can do is then we can distill the problem even further, right? And we can say that n-digit binary numbers are actually just n-element lists, right? Taken from a 2-element set, right? Because they're lists with n characters in them, taken from a 2-element set, right? In this case, the set containing the elements 0 and 1, right? Because each character has to be either a 0 or a 1 in binary, and there are n characters, okay? So we're looking for the number of n-element lists taken from a 2-element set, okay? So our earlier formula, and this is exactly what we were looking at before, right? So we came up with a general formula for this. The number of k-element lists taken from an element set is always n to the k. In this case, k we don't know, right? We have k is n in this case. We have n-element lists, but we have a 2-element set 0 or 1. So actually n becomes 2 here, and you get 2 to the k possible n-digit binary numbers, or 2 to the n because k is equal to n in this scenario. So there are 2 to the n-digit binary numbers. Okay, and therefore 2 to the n possible subsets of a set of size n of an n set. 2 to the n subsets of an n set. Okay. So effectively, the next type of question that we want to answer takes the following form. Okay, so it looks a little bit like this, right? So in how many ways can 4 students be chosen to present their posters? Okay, in how many ways can 4 students be chosen to present their posters? Okay. Now, what I mean by this is that you have four different students. Okay, let's say they've written a poster for class or whatever, and they have to come up in some order to present, right? So maybe you could have student 1, then student 2, then student 3, then student 4, or you could have student 2, then student 1, then student 3, then student 4. Sorry, give me a couple seconds. Okay, sorry about that. So yeah, you might be able to have, for example, student 1, then student 2, then student 3, then student 4. Or you can have student 2, then 3, then 1, then 4, or student 4, then 3, then 2, then 1. There are quite a few different ways that the students could come up and present their posters effectively. So the question is, how many are there in total? Okay, this is a different type of problem now. Because they're not allowed repetition, okay? So you could say that the number of ways, so effectively the sort of list that the students, you could basically say, okay, if the student, you can letter the students, so effectively student 1 could be student A, student 2B, student 3C, student 4D. And you could say that effectively each list of length 4 containing these 4 letters will effectively be, each 4 list with these 4 letters as effectively characters or members of that list could represent the order in which they come up, okay? But then the problem is that it would have to not repeat, right? Because if I repeat D twice, then he would have to come up, or he or she would have to come up twice to present, right? And that doesn't really make sense, at least in the context of it's intended to mean you only present your poster once, right? Because only one poster to present. And so obviously repeating elements here is bad. So this is not valid, even though it's a valid 4 list that we would have counted earlier on, right, with our previous formulae, okay? It doesn't work in this scenario because it repeats. So now we need to think about number of K lists without repeat, sorry. So what if the problem says that we're not allowed to repeat things, okay? Then that gives us some different results. Okay, so as I already said, the way that you can do this is obviously label students from A to D. So label students, the first thing that you want to do is probably label students either from A to D or 1 to 4, doesn't matter. From A to D, just whatever works, keep things simple. Now we know each student only presents once, okay? And so what we're actually looking for here is the number of 4 lists taken from a 4-element set in which each element appears exactly once, right? Because the 4-element set with which we're constructing our list from is just the set, you know, A, B, C, and D, okay? And we're constructing a 4 list from the elements in this set such that each element only appears exactly once, okay? That's what we're doing, okay? So we want a number, effectively, of 4 lists taken from a 4-element set in which each element appears, a 4-element set, in which each element appears exactly once. Why is this bugging out? Okay, right? Because you can't have a student coming up twice or 3 times to present, right? They only come up once to present. So we need to create some 4 list using those 4 letters, okay, which represents the order in which they come up, and you can't repeat any of the letters. That's the task. But we know that such a list, it can begin in 4 ways, okay? So such a list can begin in 4 ways. Right? If this lets me right, which it kind of is at the moment. So such a list can begin in 4 ways. So you could either start with a capital A, okay, that's the first. So you could either have student A coming up first, or student B coming up first, or student C coming up first, or student D coming up first. Okay, so there's 4 different effective orderings, actually, right? So those will correspond to 4 different orders, right? Because in each of them, a different student will come up first, okay? And then effectively, after we've locked in that first student, right, then the second student, the person who's coming up to present second, can be anyone except for the person that's already come up. So in each of these scenarios, I'll get 3 new lists, effectively, for each of them. So for example, starting with person A, I could have either as my second, as the sort of number of sort of lists in which person A comes up first, okay, and only considering the first 2 people that come up, I could have AB, right? I could have AC. I can't have AA because obviously there's no repetition, or AD, okay? So each of these sort of first people that come up will branch, each of these sort of people will give way to 3 new lists after the second person has come up, right? Because after person A, we'd have person B, person C, or person D. Okay, so there are 3 possibilities for the second person, right? And similarly for person B, we could have person B and then person A, which is a different order to person A and then person B, okay? That's a different way that they came up, okay? Or we could have BC, or we could have BD, okay? And the same for the other ones, right? So effectively, each of the 4 starting ways gives way to 3 more effective lists, right, after the second person has come up, okay? Because there are 3 possibilities, right? Regardless of who you start with, there'll always be 3 possibilities for the second person. And that will increase the number of possibilities in total, right? For the number of 4 lists taken from a 4-element set in which each element appears exactly once, that will increase the number of possibilities by a factor of 3, okay? So I'll probably just summarize that, what I just said. So in essence, just trying to get it off my iPad. Okay, in essence, second student can be anyone but the first. Can be anyone but the first. Right. So 3 different choices.
implies possibilities increase by a factor of 3. Right, as we've already seen, because for each of the 4 starting people, they'll have 3 different scenarios for effectively for the first 2 people that come up. So you can have A, B, A, C, A, D. So that's all for A, person A starting. So that's 3. Then for person B, you can have B, B, A, B, C, B, D. That's another 3. And you do 3 times effectively 4, because there'll be 4 starting ways to give you the total number of sort of orderings for the first 2 students that come up, which is 12, right? So possibilities increase by a factor of 3. And this argument is just the same for the 3rd and 4th student, except for the 3rd student, once 2 students have come up. So let's say that I have, for example, A and B. Right now I have 2 students remaining, and this student here can be anyone except for, in this scenario, A and B, okay, because they've already gone. Okay, so there are only going to be 2 possibilities there, and so that for each of the possibilities, so for each of the sort of first 2 orderings, so for each of the orderings that works for the first 2 people, so you have A, B, A, C, A, D, B, A, B, C, B, D, so on and so forth. For each of these cases, I'll get another 2 cases depending on who goes in the 3rd position, right? Because effectively, just considering the scenario where A and B go first, I could have A, B, C or A, B, D, right? Here I could have A, C, B or A, C, D. Here I could have ADB or ADC, right? And so effectively for each of these cases, I'm going to get 2 cases that branch out from that for the effectively number of sort of ways that sort of the first 3 people could come up effectively. So that's going to increase my possibilities by a factor of 2. So then 3rd student increases possibilities by a factor of 2. By a factor of 2. And lastly, the final student will increase in the number of possibilities by a factor of 1, because there's only 1 remaining option, right? So each of those sort of ways that I could have done it, that I could have sort of, each of those lists that represent sort of the number of ways that the first 3 people could come up, right? Each of them will lead to only one complete list of like the ways that all 4 of them could come up. Because once I have, say, A, B, C, the last guy has to be D, right? So this corresponds to a complete ordering, right? And specifically A, B, C, D. Similarly, if I have B, C, A, you still know that has to be D, right? So you can always fill that in. If I give you the first 3 people that come up, you can always tell me the last person to come up, which means that effectively each ordering of the first 3 people will correspond to exactly 1 final ordering, and so actually you're only increasing the possibilities by a factor of 1 in that scenario, right? Because you're not changing them, because each one corresponds to exactly 1 final possibility. So final student is effectively locked in, because there's only 1 possibility depending on what the string was before that, or what the order was before that. So possibilities increase by a factor of 1. Okay, and effectively using the product principle in essence, right? It's therefore, effectively quite obvious in this scenario that the total number of orders, so hence, total number of orders, right, is simply 4 times 3 times 2 times 1. This is actually just the product principle, right? Because we have 4 lists, okay? So we're looking for the number of 4 lists, okay? And remember, the product principle said nothing about repetition, so you can have these sorts of scenarios built into the product principle. But all that it said is that effectively, after I pick there are 4 ways to pick the first person, so C1 is equal to 4, okay? And each of those corresponds to a different list, so we're happy with that, okay? And then effectively, regardless of who I pick first, there will always be 3 ways to pick the second person. So that's unchanged. That's what the product rule or product principle required. It required that once I pick, my first person or my second person, right, say, then the second or third position respectively would have to have the same number of sort of choices to fill it up, right? So once I've chosen, let's say A as my first person, I'll still have 3 people to choose for my second position, okay? And then once I've chosen my second position, I'll always have two people to choose for my third position, okay? And each of those choices will lead to a different list, okay, effectively. And so that's why we can use product principle here, right? Where C1 is 4, C2 is 3, C3 is 2, and C4 is 1, okay? C2 is 3 because in the second position, I'll always have 3 people to choose, regardless of whatever happened in the first position, okay? And they'll give me different lists, okay? And so we can actually just use a product principle here. That's exactly what I've done. I've done 4 times 3 times 2 times 1 to give me 24 possible orders, right? So hopefully that makes sense. And what you might also realize is that 4 times 3 times 2 times 1 is also known as 4 factorial, okay? N factorial is defined as the product of the first n positive integers. Okay, of first n positive integers. Hopefully you know that. Positive integers. Okay. Okay. Right. So now we need to sort of generalize this sort of problem here that we've spoken about. Okay. So we specifically what we're doing here is we're counting lists without repetition. Okay. So we want to know how many ways there are to count lists without repetition in general, so that we don't need to repeat the argument every time. Okay. So let's just have a look at that. So counting lists without repetition. Okay, so if we have a list and we don't allow repetition of elements, we call it a permutation. So a list without repetition, okay, is said to be a permutation. right? And we arbitrarily define a k permutation to be a permutation of length k. So just a list that doesn't allow for repetition of length k. Okay. Well, we'll also define an n permutation of an n set. So effectively the number of ways that I can permute the elements of a set of size n, okay, which effectively the number of ways that I can put them in a list without repeating, is said to be, it's just defined as the permutation of a set, or a permutation of the set, right, that we're considering. So an n permutation of an n set is called a permutation of the set, or a complete permutation of the set, depending on whatever language you use. Okay. So for example, if I were to take a set with 4 elements inside and say, okay, if I were to put these in a list and not repeat them, how many ways would there be to do that? Well, there's going to be 4 factorial. Basically, this is exactly the same problem if we were to consider 4 permutations of a 4 set. Effectively, it's exactly the same problem as what we just went through with the students, okay? And so it will give you 4 factorial of 24. Okay, in general, it will give you n factorial. For an n permutation of an n set, there'll always be n factorial n permutations of an n set, effectively. Okay. And now here's the main formula here that we need. So the number of k element lists without repetition taken from an n set, is simply effectively n in brackets subscript k. Right. It is effectively just n in brackets subscript k. Okay, so that's just sort of the notation that we use to represent the number of k element lists without repetition taken from an n set. Okay, so the number of lists that we can make of length k using elements from a set of size n. Okay, is written like this. Okay, and actually in sort of notation, it's the way that you compute it is as follows: so n factorial divided by n minus k factorial, which is in other words n times n minus 1 times all the way down to n minus k plus 1. Okay, because n factorial is n times n minus 1 times n minus 2 all the way down to times 2 times 1, but everything after n minus k all cancels out. Okay, you'll get n times n minus 1 times n minus 2 all the way down to times n minus k minus 1, and then that all cancels out with the denominator. So n minus k times n minus k minus 1. So this cancels out, right? Everything after that will cancel out. And so the last thing that won't cancel out is n minus k plus 1. And you'll effectively just get a product, n times n minus 1 times n minus 2 all the way down to n minus times n minus k plus 1. That is the number of k element lists without repetition taken from an n set. Okay, and let's think about this, right? Suppose that I have a set of 4 elements, 1, 2, 3, and 4. Okay, so suppose for example that I have 5 students, right? And they need to come. They have posters. They need to come and present their posters, but on a specific day, only 2 of them can come up, right? How many ways is there for that? Like, how many different sort of ways are there for those 2 students to come up? Well, there's obviously going to be sort of 5 choices for the first student that can come up, right? If we letter the students or number the students from 1 to 5, there'll be 5 students that can come up first, and then given that whichever student has come up, there'll always be 4 students that come up next. Okay, so the total number of effectively orders for that specific day will be 20, right? So there'll be 20 different sort of orders of which those 2 students can come up to present their posters on a specific day. Okay, and it's 5 times 4, right? Because we have 5 students at the beginning, right, to present their posters. Then once one person's presented, there'll only be 4 remaining to present. Okay, so then in the second position of that day, there'll be 4, right? But there's only 2 positions, so we do 5 times 4. We don't need the times 3 because there's not 3 people presenting on that day. There's only 2. Okay, if there was 3 people presenting, then after the first 2 people have presented, there'll be only effectively 3 people left and to present for and so in the third position there'll be 3 options, right? No matter what's chosen first and second. Okay, but in this specific case, we're only saying that there's 2 people that can present on this day. Okay, and so you'll have 5 times 4. But notice that 5 times 4 is actually also 5 factorial divided by 3 factorial, right? And we can also write that as 5 factorial divided by 5 minus 2 factorial, right? And 2 specifically is the number of people that are allowed to present. Okay, and that's not a coincidence. That is exactly the same as the formula that we have up there. Okay, simply because effectively, in general, if I have a k element list taken from an n set, right, then I might cut off that list somewhere. So instead of just being n factorial, as we saw for our problem before, which we had 4 factorial, it'll effectively be n factorial divided by something else factorial to cut off the last part of that string, right? So if I had 3 people presenting, right, then it would be 5 times 4 times 3. Okay, if this lets me write. 5 times 4 times 3, and 5 times 4 times 3 is just 5 factorial divided by 2 factorial, or 5 factorial divided by 5 minus 3 factorial. Okay, so hopefully you can see, why this is the case, right? Because first of all, there are 5 students. Okay, so there would be if all 5 of them were presenting in one day, there'd be 5 factorial ways for them to present. Okay, but if we imagine like all the possible ways that they could present, so like let's say it was A, B, C, D, E, right? And we're imagining that we cut off the last three people, okay? There'll be three factorial sort of arrangements of these people that we don't care about, because the only thing that we're looking at is this, right? The first two people, okay? So you'd effectively do 5 factorial, okay? And then divide it by 3 factorial to get rid of those last three spaces, okay? And 3 factorial is also 5 minus 2. So you take the number of spaces that you care about, you do 5 minus that, you factorial it, and then you put it in the denominator, you do 5 factorial divided by that. Okay, and that's exactly where this n factorial divided by n minus k factorial comes from. Okay, specifically, yeah, it's just the number of k permutations taken from an n set, effectively, right? So hopefully that makes sense. And it also works very nicely. Okay, because sorry, let me just rub all this out. It works very nicely because if we're looking at the case where we're taking the number of n permutations of an n set, well, I told you that was n factorial. Now we can easily derive it. Okay. The number of n permutations of an n set, okay, would be effectively n in brackets subscript n, simply just n factorial divided by n minus n, or factorial, which is n factorial divided by 0 factorial, and 0 factorial is defined to be 1. So it's just n factorial divided by 1, which just gives you n factorial, which is exactly the truth, right? That if I have 5 people presenting on a specific day, okay, then there'll be 5 factorial ways, given that there are only 5 people to present, right? To order those sort of presentations. There'll be 120 possible presentations because it's 5 times 4 times 3 times 2 times 1. Okay, so that basically collapses to n factorial in the special case where we're dealing with n permutations of an n set, or taken from an n set. So effectively, n element lists without repetition taken from an n set. There'll be n factorial of them. If we're looking at k element lists taken without repetition from an n set, then we have n factorial divided by n minus k, or factorial, which is actually also known as npk. Okay, p stands for permutation. So npk is n factorial divided by n minus k, all factorial. Okay, so the next type of question, there are two more big type of questions that we need to answer. I appreciate this video will probably be long, but hopefully it'll be sped up and won't be too bad. Okay, there are two other types of questions that we need to answer. Okay, the first of which is as follows: suppose that you play a pick 6 lottery. Okay, so you're playing the lottery. You have to pick 6 numbers from 1 to 40. Okay, by specifying 6 different numbers from 1 to 40. Okay, how many different lottery tickets exist effectively? Okay, so how many different lottery tickets exist? Right, well, you might think, okay, well, there's 40 numbers, okay? So I have 40 options for the first. Regardless of whatever I choose for my first, I'm going to have 39 remaining numbers to choose from. So why is it not just 40 factorial divided by 34 factorial? Okay, well, it's not this, because you can choose the same choice in 2 different ways, or multiple different ways, right? Effectively, let's say that my 6 number choice was 1, 2, 3, 4, 5, 6, okay? I could choose it in that specific order, or I could choose 6, 5, 4, 3, 2, 1, okay? In that order. So I could choose 6 first, then 5, then 4, then 3, then 2, then 1. These correspond, though, to the same lottery ticket, because once I hand in the lottery ticket, it will look exactly the same. Okay? So I can't just do this 40 times 39 thing, because it gives you a number of permutations, but that clearly overcounts, because there are multiple different ways of filling in, multiple different orders of which I could have filled in the same 6 numbers. Okay? So we need to think a little bit more about that. Okay? And now what we need to do is we need to turn to sets, okay, where order doesn't matter, right? And I say order doesn't matter because I could have filled in 6 then 1, or 1 then 6 gives me the same lottery ticket. So order here doesn't matter. So instead of lists now, we need to think about sets. Okay? Specifically, a lottery ticket is effectively a size 6 subset of the set from 1 to 40. A lottery ticket is a subset of, the set from 1 to 40, because we're choosing numbers from 1 to 40. Set of natural numbers from 1 to 40, okay? And the size of it is 6, so it's of size 6. Okay, so then if we know, okay, how many subsets of a 40 element set are there of size 6, then we answer the question. Okay, but we actually want to look at a more general question, which is how many k subsets are there of an n set? So how many subsets of size k are there of a set of size n? Because then that gives us a more general answer, which we can just apply to this specific case, and we've answered the question. So then the next question within the question is effectively how many k subsets are there of an n set? K subsets are there of an n set? So how many subsets of size k can you make from a set of size n? Okay, so we'll denote that number. Okay, we don't necessarily know what the number is, but there'll be a number of ways to do it in general, and we'll denote it as, so we'll denote this number, whatever it may be, as effectively nk like this, right? So nk within brackets. Obviously, many of you probably know that as n choose k. That's how we say it. But effectively, if you didn't, then don't worry. It's effectively just n on top of k within these two brackets like that. Okay. So this is just a way that we denote the number of k subsets of an n set. Effectively, like we're going to say we don't know what the number is, but we'll denote it using this notation. Okay. Now we know the number of k permutations of an n set. Okay, that's quite simple. Because we know that the number of k permutations of an n set is just effectively n factorial divided by n minus k factorial. So k permutations of an n set, right, is just n subscript k like this, which is just equal to n factorial divided by n minus k all factorial, for the reason that we already discussed. Okay? Well, we know that that's the number of k permutations, obviously, but, you know, if we really wanted to derive that, okay, then what we could do is we could first find the number of k subsets, right? one way which we could derive that is by finding the number of k subsets of an n set, okay, right? So the number of possible subsets of length k of an n set, which we denoted as n effectively n choose k is what we say, right? So we could first find the number of subsets of an n set, okay, of which there are going to be that number, which we don't necessarily know what it is at the moment. So we can find k permutations of an n set by first finding the number of k subsets, right, of an n set, right, of which we know there are n choose k. Okay, and then after that we can effectively line each of the k elements in those subsets up, and then find how many ways we can order them, which is simply just going to be k factorial, right? Okay, and then we can line those k elements up, and then line those k elements up in a particular order. So basically, we take those k elements, which are just in a new set, and we're asking how many k permutations are there of that k set. Well, there's k factorial, as we already discussed. Okay? In a particular order, of which there are k factorial orders. Okay? And this will give us the number of k permutations of an n set, right, in a different way, by first finding all the possible subsets of size k, okay? So for example, if I have a set of size 4, the number of subsets of size 2, okay, we don't know necessarily what it is, but one example will be 1, 2, and that's the same thing as the set of size with 2, 1 like this, okay? So those are two of the same subsets, okay? So whatever our count is, it has to effectively make sure that this is counted only once and not twice, effectively. And so, you know, we take all the subsets of size 2, and then we order those, we place them, we find the number of effective, we place them in a new set like this, so this is just a subset of size 2, and then we find how many 2 permutations are there of that 2 set, or how many k permutations are there of that k set, and we already looked at this. The general formula is just this. It would be, instead of n subscript n, it would be k subscript k, right? But effectively, it's just k factorial divided by k minus k all factorial. K factorial divided by 0 factorial, which is k factorial, right? Because 0 factorial is defined to be 1. Okay? So, that's another way which would be able to find the number of permutations of length k of a set of size n, okay, by first of all finding the number of subsets of length k and then doing effective permutations on those subsets, okay, and using the product principle, okay, right, by the product principle, right, we know that there'll always be effectively n choose k choices, right? We don't necessarily know what the number is, but we know that there'll be that many choices for the number of k subsets from a set of size n. We know that will always be the number, okay? And each of those choices will lead to effectively a different subset, okay? So a different permutation once we do the k factorial stuff, right? And then after we've chosen that, there'll always be k factorial ways to arrange the k subset, right? So there'll always be k factorial k permutations of the subset, okay? And so, because, you know, those are independent of each other, right? And they always lead to effectively different, you know, final k permutations of the n set, that means that we can multiply them effectively via the product principle, okay? So by the product principle, there are thus, right? So we can multiply them to find the number of total k permutations of an n set. N choose k multiplied by k factorial k permutations of an n set of an n set. But we also already know that there are, you know, this, but we know that there are n in brackets subscript k permutations of a subset, right? We already know this, okay? from what we've already seen. So we can equate the two because they give you the same number. So effectively n choose k times k factorial is equal to n subscript k like this, which is equal to n factorial divided by n minus k all factorial. And then when you divide by k factorial, obviously it can never be 0 for integer k, then for positive integer k, then what you get is that n choose k is equal to n factorial divided by k factorial multiplied by n minus k factorial. And we've derived a formula to calculate now the number of k subsets of an n set, specifically n choose k, which I'm sure you're all familiar with, as being n factorial divided by k factorial times n minus k factorial. Okay? So in our example, okay, we wanted to find the number of subsets of size 6 of a set of size 40, so that's the number of lottery tickets. So what we do is we do 40, choose 6. Okay? And this number will be quite large, as you'd probably imagine. It's going to be 40 factorial, right, which is insanely large. Then you're dividing that by, you are dividing it though, by 34 factorial, so you're cutting off a lot of that large stuff, and then multiplying that by 6 factorial. Okay? So 40 choose 6, it's still going to be a large number. What is it going to be? It's going to be 3,838,380. Okay? So effectively, that's the number of lottery tickets that are possible if you have 40 numbers to choose from. And how many different lottery tickets are possible if you have 40 numbers to choose from and you have to choose 6 of them? There are exactly 3 million different lottery tickets. Okay? Nice. So you've answered the main question there. Another just note is that these sort of n choose k things here, we call them, this is the sort of special number here, n choose k. Any integer which can be effectively written in this form, so that is n choose k for some choice of n and k. Okay, any integer which can be represented in like this sort of form as n factorial over k factorial times n minus k all factorial is effectively called a binomial coefficient. Okay, the reason why we call them binomial coefficients is because these numbers, specifically, as I'm sure you're aware from A-level study and maybe even from GCSE further maths, these numbers, n choose k, they are related to the binomial theorem, okay, quite closely in things like Pascal's triangle, and effectively, it's the main link is obviously to the binomial theorem, and so we call them in general binomial coefficients. So these numbers, n choose k, all numbers that can be represented as n choose k for some choice of n and k, are called binomial coefficients, and that's just the name that we give them in combinatorics. The link to the binomial theorem is not important for this video, but it is there, and you can definitely search it up, and there'll be lots and lots of stuff on it. Okay. Another important thing to note is that we say a combination is a subset or unordered collection of distinct objects. Okay. And obviously repetition is not allowed. Okay, because in sets there is no sense of repetition, right? You can repeat elements, but you keep the set the same. Okay, that's annoying. I'll just do this on my computer instead. Hold on. Okay, so effectively, we say, I think it's important that I write this. So we've already been introduced to lists, permutations, now we have combinations, okay? So we say that a combination is a subset or unordered collection of distinct objects. Or unordered collection of distinct objects. Okay? And obviously, repetition keeps it the same. Distinct objects. But for example, in the case of the lottery ticket, that is effectively a subset question, as we managed to figure out, right? So looking for the number of subsets of size 6 from a set of size 40, okay? But obviously there was no repetition. You can't repeat the same number twice in the lottery, okay? You need to choose 6 different numbers, at least in that lottery, okay? In that specific lottery, you have to choose 6 different numbers, okay? And so obviously there's no repetition of anything, okay? So that's why it's effectively this type of problem. It's a combination problem, okay? And that's also why as well, some people write n choose k as nck, and C stands for combination, or really choose, but effectively you can think of it as combinations if it helps you remember. Okay, so the order doesn't matter, right? Because I could choose the same 6 numbers in multiple different ways, right? If I choose 1 first, then 2, then 3, then 4, then 5, then 6, that's different to me choosing 6 first, then 5, then 4, then 3, then 2, then 1. But it's the same choice overall, okay? And so the order at which I choose the number doesn't matter, okay? And obviously repetition of numbers is not allowed for these types of problems, okay? Nice. So now we move on to the final type of problem that I want to cover in this video, which is definitely the hardest type of problem, okay? So you've got to be quite attentive for this. So try and answer this question. It's quite a difficult one. So a store, right, offers 30 flavors of donuts, or 30 donut varieties. So 30 donut varieties. So 30 flavors of donuts, varieties. How many different orders of 12 donuts are possible? Okay? How many different orders of 12 donuts are possible, right? Now, because obviously the numbers here, 30 and 12, are quite big, you're actually going to get a number that's very, very large, okay? In fact, if I remember correctly, I think the number is around in the billions, okay? So there's going to be billions of possible orders, okay? So in this scenario, okay, before we answer this question, I want to answer a smaller related question, okay? So let's say that there were only four varieties of donuts, 4 flavors of donuts, and you wanted to find the number of orders of 3 possible donuts, okay? So if there are 4 donut varieties, let's say, I think in the book it mentions Boston cream, so we'll say that's effectively capital B, chocolate, right, that's capital C, right, glazed donuts is capital G, and maybe maple is capital M. Okay, so basically those are the 4 flavors of donuts that we have, and we are looking for the number of possible orders of 3 donuts. Well, there are a few different cases, right? You could order Boston cream 3 times. Okay, so maybe you just really like that flavor, you just want to get it the same donut 3 times. Fine, no problem. Or you could get 2 Boston creams and 1 chocolate donut. Okay, that's the same though as if I order a chocolate first and then 2 Boston creams. So the order at which I make the order in doesn't matter. Okay, because it's the same order, right? If I get 3 of the same donut, it doesn't matter which order I choose the donut in, right? Which order I order them in. But specifically, if I have a chocolate and then 2 glazed donuts, that's the same as if I get a glazed donut first and then two glazed donuts first and then a chocolate, right? It gives me the same order effectively. So we don't care about the order here. So order doesn't matter, but we do allow for repetitions, which makes this hard because we are allowed to get the same type of donut more than once. Okay, and obviously there'll be different types of donuts. So 2 Boston creams, 1 glazed, 2 Boston creams, 1 maple. And when you actually do all the possibilities, you won't get that big of a number actually. In this specific case, you'll get exactly 20 possible orders. So if you have 4 donut flavors and you want an order of 3 donuts, there are 20 possible orders, okay, that you can make. And that's just by listing them out. So you can continue doing that yourself, okay? I haven't necessarily used any intelligent proof method yet, okay? But a thing to note is that effectively, you might think, hold on, I've written this in set notation, but for a set, repeating elements keeps the set the same, right? Well, actually now we're dealing with things called multi-sets, okay? So multi-sets, they are effectively sets, they're like the brothers of sets, where we allow repeated elements. Okay, multi-sets are defined as sets that allow for repetition of elements. Defined as sets that allow for the repetition of elements. Okay, so for example, I could get the same donut 3 times, or I could get the same donut twice and then a chocolate. Doesn't matter, right? All I'm saying is that each order is represented using a multi-set, right? Each order that I make to the shop is represented using a multi-set. And these are just sets that allow for repetition, because in this scenario we need to be able to encode repetition somehow, because like I said, I can get the same type of donut twice or even 3 times. Okay, if the order is 3 donuts, if it's like 10 donuts, I get the same type of donut 10 times if I want, right? So that's a possibility, okay, even though possibly quite improbable for myself, improbable. But you know, it's their possibility, right? And so we're not really taking into account necessarily how probable it is, just asking for the number of possibilities. Okay, so these are multi-sets, okay, they're just sets that allow for repetition of elements, right? And we still use, perhaps confusingly, but you know, it can be easy to tell whether a set is a multi-set or not from context. Okay, so we still use the sort of set braces to represent multi-sets. Okay, to denote multi-sets as we would sets. Okay, and the only way to distinguish between them is via context. Okay, so at least in the way that sort of we've defined them here, you could, I guess, have some sort of different opening way to define multi-sets if you wanted to. You didn't need to use the same notation as sets, but we do in general, I think. So just notation, and it's a bit annoying, but context should make it clear what type of set you're looking at, whether you're looking at a set or a multi-set. Okay, right. So now what we're looking for, effectively, then we know now we've introduced multi-sets. The question boils down to how many k multisets can be taken from an n set? So how many multisets of length k can be taken from an n set? So we define this thing here, so like a double choose, to mean to be the number of k multisets taken from an n set, which we don't know just yet. Okay, to be the number of k multisets taken from an n set. Okay. Now what we do know though, we do know that specifically from the example that we just looked at, the number of 3 multisets, so multisets of size 3 taken from a set of size 4 is actually 20. Okay, so maybe we can use that to check against later on. Because effectively each of these orders of 3 donuts is a multiset, right, as we've already discussed, of size 3. Okay, and there are 4 possible choices for each donut, effectively, right? You could have a Boston cream, a chocolate, a glazed, or a maple. Okay, in the initial question, we want to find effectively what we're looking for in this question is we're looking for this coefficient, this sort of thing here, which is 30. The number of multi-sets of size 12 from a set of size 30, which is just this, effectively, right? So they sort of double choose 30 and 12 inside, okay? Cool. So we need to somehow find a way to derive this then, which is a little bit trickier actually than the first way that we derived n choose k. So if you're not sure what the answer is, try and derive this. Okay, stop the video now. Try and derive the number of k multisets from an n set, because this is actually good practice really. If you're not familiar with this type of concept, then it's good practice actually for the type of question you might get in an interview. Okay. Because this is a little bit less well known, even though it's still quite well known. To be honest, if you do combinatorics, it will come up. But still, if you have never seen this, do practice. Try and find that derivation and try and answer the question about the donuts. Okay. Now I'm going to assume that you've stopped the video because I'm now going to continue and go with and prove the general form for this number that we want. Okay, which is just n double choose k effectively. Right. So what we're going to start by doing is drawing k donuts in a row. Okay, so that just represents, we haven't necessarily chosen the flavor of each of the donuts. We're just choosing the donuts, right? We just have the donuts in a row, okay? Ready to sort of choose which donuts you want of which flavor, okay? So we start by drawing k donuts in a row. I'll represent them using stars, just to keep things simple. Represented by stars. Okay, then what I'm going to do, okay, so I just have basically k donuts, like k stars, right, in a row, representing my donuts, and I'm going to basically insert these vertical lines. Specifically, I'm going to insert n-1 vertical lines, okay, where n is the number of flavors of donuts that I have. I'm going to insert n-1, because when I insert n-1 lines, I make n different regions. So here I've inserted 2 vertical lines, and I have 3 different regions here that I created, okay? And this first region could be the first flavor, so flavor 1. This region here could be flavor 2, and this region here could be flavor 3, okay? And now what I've done is I've basically chosen which donuts are going to be of which flavor, okay? So this could be my first flavor, so there's 1 donut of this flavor, 1 donut of this flavor, and 3 donuts of this flavor, okay? And now what will give me my different multiset is the different ways that I could sort of put those 2 vertical lines in basically, in sort of this I guess, arrangement of 5 donuts, right? So the number of ways, so each different sort of way that I could sort of put 2 vertical lines in this arrangement of 5 donuts corresponds to a different order. Okay? Okay. Right, so now we have that idea, okay? We can try and make it a little bit more rigorous, okay? Or a little bit more precise. So I'm also gonna write here, insert n-1 bars, insert n-1 vertical lines to represent n flavors or n regions, right? And the number of flavors of each, and the number of donuts of in each region corresponds to the number of donuts in that specific flavor. Number of donuts. I'll say the number of donuts in region I, right, corresponds to the number of donuts of flavor I. To the number of donuts in the given order right, that are of flavor I. If we number the flavors, okay, if we number the flavors from 1 to whatever we need, 1 to n. If we number flavors, doesn't say if we know, it says if we number the flavors, sorry, what I meant. If we number the flavors, just being a bit lazy there, if we number the flavors from 1 to n. Okay, so hopefully you get the idea. We have these number of stars represents just the number of donuts without having chosen flavors just yet. Then I introduce some number of bars, n-1 specifically, where n is the number of flavors that I have, to give me these n regions, and each of the number of stars in each region corresponds to the number of donuts of that specific flavor. Okay, if I number the flavors from 1 to 3. Okay, so hopefully that makes sense, right? Well, okay, fine. So let's suppose then that I have k spaces for the donuts. I have k donuts, right? So I'm going to have k spaces for my donuts, right? So that's 1 space, that's 2 spaces, that's 3 spaces, that's 4, right? And so on. I'm going to have k spaces, okay? And then, effectively, the number, effectively, of places, the number of effective spaces that I have for my bars is exactly going to be n-1, right? Because, effectively, if you can imagine that I just have, if I just insert 2 bars in here, right? I've inserted specifically n-1 bars in, okay? So if I imagine each of these sort of places where there's either a star or a bar corresponding to a place, right? Then there would be k plus n-1 places in total, right? So let's say I have something like this, right? So I'm going to have k star. Let's say that I have 4 stars, 1, 2, 3, and 2 bars. Okay, so it could be something like this. I could put my stars out like this, okay, and then I could put 2 bars in like this, okay. And that in total is going to give me 6 spaces, okay? Even though, right, there are different ways that I can arrange those 6 spaces, okay? There's in total going to always be k plus n minus 1 spaces, right? Where k represents the number of donuts I have, okay? So k donuts, and then n minus 1 spaces for the bars, right? So in total, I'm going to have k plus n minus 1 spaces in total, effectively. So being used up, right? If you count a space, that just mean something is there, whether it be a bar or a star. So there are, I use up k spaces for donuts, effectively, or stars, for donuts, and n minus 1 spaces for bars, and n minus 1 spaces for bars, so that I use up k plus n minus 1 spaces in total. So the number of spaces I have is simply k plus n minus 1, right? So now let's introduce a set, okay? Let S be the set of natural numbers from 1 all the way to k plus n minus 1, okay? Now, I have some number of spaces already. This is the number of spaces that I'm going to use up. So let's say that I have, in the case that I have there, 5 donuts, okay, and 3 flavors. So I'm going to have, in total, I'm going to have 7 spaces, right? Because I need to place 2 bars. So I'll have 7 spaces, 1, 2, 3, 4, 5, 6, 7. There'll be 7 spaces, right? And what I can do, okay, is I can effectively choose where my bars go from there, okay? I'm going to have, let's say, in that case, I'll have 2 bars. I'll always have n minus 1 bars, though. So what I'll need to do is I'll need to find a subset. How many subsets of this specific set here, which is of size k plus n minus 1, so each space is given a number. That's 1, that's 2, that's 3, that's 4, that's 5, that's 6, in this case that's 7, okay? But it will always just go from 1 to k plus n minus 1, okay? So how many subsets of a set of size k plus n minus 1 are there of size n minus 1, okay? And that gives us the answer, because then, at that point, that chooses 2 spaces to put my bars in, okay? Right? So if I get my subset 2, 4, for example, so 2, 4 here corresponds to me putting the bars in place 2 and 4, maybe 3, 5 corresponds to me putting the bars in place 3 and 5, okay? Then I'll remove the bars from place 2 and 4, right? And effectively, any subset of size 2 is going to correspond to sort of 2 positions where I put my bars, okay, from the set from 1 to k plus n minus 1, okay? And so the question then becomes, how many subsets of size n minus 1 are there in a set of size k plus n minus 1? And this question is exactly the question that we answered in the previous part of the video. And if we go back, we'll see that in general, there are n choose k subsets, or subsets of size k, from a set of size n, right? So there are, right, k plus n minus 1 choose n minus 1 subsets of size n minus 1, okay, which represents the positions where I put my bars in, okay, in a set of size n plus k minus 1, which represents all the total spaces I have, or k plus n minus 1, since we're doing the k donuts plus the n minus 1 bars to get my total number of spaces, okay? So, okay, and all the different ways that I could, put my bars in effectively gives me all the different orders, okay? And so this effectively is just the number of orders of k donuts, effectively, if there are n flavors to choose from. Okay, how many different orders of k donuts are there if there are n flavors to choose from? Which effectively is exactly the same, okay, as n double choose k. Okay, so we've now proven that actually this is equal to, specifically, k plus n minus 1 choose n minus 1. And to check this, we can go back. You were saying that 4 double choose 3 is 20. So 4 double choose 3 would be 4 plus 3 minus 1, so that's going to be 6. Choose, what's it going to be? N minus 1, so 3. 6 choose 3 is 6 factorial divided by 3 factorial times 3 factorial. There's 6 times 5 times 4 divided by 3 times 2 times 1. So that's going to be 120 divided by 6, which is indeed 20. Okay, so that's looking very hopeful. And if the proof is correct, which it is, then this, we've successfully shown that, in general, this multi-set number, so the number of k multi-sets in a set of size n, is specifically k plus n minus 1, choose n minus 1. Okay? Let me write that in the next section. That is probably the most important thing. If you manage to get that by yourself, also very well done. That's quite a tricky proof. Maybe something that you might see in an interview as well. But obviously, I think it's quite well known, so probably not. But still, good practice anyway if you got it. Okay. So, the number, as we've already ascertained here, of k element multisets, right? Multisets, right? Taken from an n element set is exactly n double choose k, which is just k plus n minus 1 choose n minus 1. Okay? And in this, for multi-sets, right, the order doesn't matter. So in other words, if I'm choosing a specific order of donuts, right, I could choose 2 chocolates, then a glazed, or a glazed, then 2 chocolates, right? Different order of choice, but the same order effectively from the shop. So the order of which I choose the donuts doesn't matter. And repetition here is allowed, okay? Because I can choose, 2 chocolate donuts, 2 glazed donuts, 3 chocolate donuts, 3 glazed, however many I want, as long as sort of it's not more than the number I'm allowed to choose for the specific number of donuts I'm considering, right, in my order. So repetition is indeed allowed, right? So in general, for multi-sets, order doesn't matter because they're sets, but repetition is allowed, okay? So yeah, there you go. The number of k element multi-sets taken from an element set is this n double choose k plus n minus 1 choose n minus 1. So the answer to the initial problem, which I posed here, is just a number of 12 multi-sets from a set of size 30, which is 30 double choose 12. So 30 double choose 12, which is going to be what? 30 plus 12 minus 1, so that's going to be 41. Choose 29. Okay. Now, when you do that, you're going to get probably quite a big number. Yeah, you're going to get 7,898,654,920 different orders of 12 donuts if there are 30 flavors to choose from. Okay. 7 billion. So 7.9 billion orders. Okay. Which is kind of crazy. But the fact that we're even able to sort of get that number is quite nice. Okay. Because obviously no one is ever going to be able to count all of the possible orders by hand, even with a sheet of paper, probably. Only a computer would be able to do that. But these sorts of formulae came out before that, I think. And so it's very nice that maths actually is able to give us this very neat formula that effectively corresponds to these types of problems in counting. Okay, so again, combinatorics all about being efficient with counting, and that's exactly what we've done here. Okay, so we're pretty much at the end of the video. I just want to highlight the 4 different things that we've looked at. So in terms of a table, there are things that you might look for in sort of certain combinatoric problems are problems where order matters, okay, or problems where order doesn't matter, okay. So order mattering or not mattering is something that you have to be able to sort of ascertain from the wording of the problem, okay. So an example where order does matter is like a password, okay. If you swap any 2 letters of a password, okay, as long as they're not the same, then effectively you get a different password. So password starting with A and then B is different from password starting with B and then A. So order there does matter. So if you're dealing with passwords, you're automatically in that column there. If the order doesn't matter, you might be dealing with something like a lottery ticket, right? Where you could pick 1 then 2 or 2 then 1, but the choice is the same ultimately, okay? So the other thing that we consider is repetition. So is repetition allowed? Okay. So for example, the first case we looked at was passwords. You're allowed to repeat uppercase letters, okay? So that's where a case where order would matter and repetition would be allowed. And obviously there we saw that the number of effectively passwords, the number of k-lists chosen from a set of size n, right, where effectively repetition is allowed is n to the k. Yeah, so that's where order matters and repetition is allowed. But also there are certain scenarios where repetition is not allowed, right? Such as when you're playing the lottery, okay, right? You can't just repeat the same number, okay? At least in our case, you have to choose different numbers, okay? So repetition is out of the question, okay? So, and in that lottery case, that was over here, right? So order doesn't matter, and repetition is not allowed. So you get n choose k, right? That's the number of effectively k subsets there are from a set of size n. The number of k multisets from a set of size n is this specific case, so order doesn't matter and repetition is allowed. So that's n double choose k. And then the scenario we're looking at with the presentation, right? So the number of k permutations from an n set is n in brackets subscript k, which is n factorial divided by n minus k all factorial. So this is the table that you should already know these 4 concepts pretty well. They come up quite a lot in basic counting problems, okay? And like I said, although in an interview you're not going to get probably a very simple counting problem which just involves sort of something like this, but it might be a step in the problem, or it might be the problem might be require some logical thinking first, and then you have to use this sort of thing, and then it'd be easier if you knew this, right, to do the second part of the problem. But it won't just be this, right? I think that's a little bit too simple. But yeah, definitely these sorts of ideas are helpful to know. And so yeah, and so effectively these to specify here, we're dealing with problems, right, where k objects are arranged from a set of size n. Okay, so for any problems where k objects are arranged, so for problems where k objects are arranged, okay, this is me, right, are arranged from a set of size n, okay, we can use the above table to determine which sort of specific formula we should use. So we can use the above table to help us. Okay, I think it's definitely worth memorizing these things. Okay, n to the k, n choose k, right, and how to compute those. It's worth memorizing them. Okay, because it just makes things computations so much quicker for sort of simple counting problems or parts of a problem that involve simple counting. Okay, and like you want to sort of be quick and not waste time too much on simple counting things. You want to sort of worry more about sort of the hard logical other parts of the problem, right? Yeah, like all the new stuff that they might ask you that you can't really prepare for. But this stuff, basic counting, you can prepare for because you just know them, right? You just know the formulae effectively. And you should really also know when to apply each of these. Okay, you really cannot incorrectly apply them, because if you do that, you'll get the wrong answer, and you won't believe actually how much this does happen. People will like just will know the different things and misapply them. Because right, yeah, sorry, I forgot that. For example, order doesn't matter, so actually I'm overcounting by applying n to the k or something like that, right? Like you need to be able to read the problem, understand the context of the problem, and then using that context effectively ascertain which one of these four things it'll be. If it's a simple counting problem where you're arranging k objects from a set of size n, okay? And effectively, hopefully, once you've done that, these sorts of problems will become basically routine computation for you, okay? Okay, well, thank you guys very much for watching. That has been basic counting cues, typical counting questions, and the product principle, okay? See you guys in the next one. Goodbye.